Good morning, students. In previous class of this chapter, Chemical Kinetics, we already covered rate law and rate constant, characteristics of a rate constant, unit of a rate constant, then order of a reaction, characteristics of order of reaction, types of order of reaction, and some numerical problem relating to it. Today, that is in class 3 of this chapter, we cover molecularity of a reaction, characteristics of a molecularity, types of a molecularity. Then the first long question of this chapter, that is kinetics of zero order. I repeat again. In this chapter, that is chemical kinetics, for council point of view, two long questions are there. One is kinetics of zero order and one is kinetics of first order. So today we cover the first long question, that is kinetics of zero order. So let us start one by one. That is, first we discuss molecularity of a reaction. So before going to the molecularity of reaction, solve one problem relation to the previous class, that is order of a reaction. One question is that the rate of a gaseous reaction becomes half. Mark that question. One question is there. The rate of a gaseous reaction. The rate of a gaseous reaction becomes half when volume of the container becomes double. Then calculate the order of a reaction. Mark that a gaseous reaction is there. Then it has been observed that according to question, the rate becomes half when the volume of the gaseous container is double. So we have to predict the order of reaction. Let us consider a gaseous reaction. Answer. Let us consider a gaseous reaction A give rise to product, and where order of the reaction is small n. Then rate of reaction, that is R, is equal to K into A to the power n, where small n represents order of reaction and A is the reactant. Suppose concentration of reactant is small a moles per liter, then R is equal to K A to the power n, equation 1. Then according to question, what is the question? When volume of the container is double, for the gaseous species, then concentration reduced to half. If concentration reduced to half, then according to question, rate becomes half. That means R by 2 is equal to K A by 2 to the power n, or it is equation 2. If we divide equation 1 by equation 2, dividing equation 1 by 2, we have that is R by 2 is equal to K A to the power n by K A by 2 to the power n, implies that 2 or 2 to the power 1 is equal to cancel 2 to the power n, implies n is equal to 1. That is, the predicted order, the calculated order is first order. It is a type of problem relating to order of reaction, 2 mark question. Then switch over to molecularity of a reaction. Then we switch over to next one is the molecularity of a reaction. Molecularity of a reaction. It is the important one for this chapter. It is a 2-mark question as well as a 3-mark question. If in the question paper define molecularity, then we write only definition. On the other hand, if a question is write short notes on molecularity of a reaction, then we write definition, explanation, characteristics and types of molecularity. So discuss one by one. What do you mean molecularity reaction? It is defined as the number of atoms, ions or molecules which collide effectively at a time among themselves to bring about a chemical reaction is known as molecularity of a reaction. That is, I repeat again, it is defined as the number of atoms, ions, molecules which collide among themselves at a time effectively to bring about a chemical reaction is known as molecularity of a reaction. Then we discuss some explanation relating to molecularity. There are some reactions are there which complete in a single step, that is known as simple reaction or elementary reaction. Some reaction proceed a number of steps, that is known as a complex reaction. Each step of a complex reaction is known as mechanism of a reaction. It has been observed that in case of a simple reaction, the total number of atoms, ion or molecules collide themselves at a time to bring about a chemical reaction. That means, which proceed through in a single step reaction. That means, for an elemental reaction, molecularity of a reaction nothing but sum of the coefficient of a balanced chemical equation which is represented by a chemical reaction. But that means for a simple reaction, for an elemental reaction, order of a reaction is equivalent to molecularity of a reaction. But for a complex reaction, molecularity of reaction is different from order of a reaction. It is a theoretical value. It is calculated from simple reaction or elemental reaction. For complex reaction, one is not able to calculate the molecularity of reaction. And it has been observed that the complex reaction which proceed a number of steps, then each steps of a complex reaction, the rate is different. One is slow one is faster one. So it has been observed that the slow step, the reaction which proceeds slowly, that is known as a rate determining step. So slow step reaction is the rate determining step. Then we discuss characteristics of molecularity. Next we discuss characteristics of molecularity. Characteristics of molecularity. 3 to 4 points are there. We discuss one by one. Point 1. Molecularity refers to single step reaction. It refers to a single step reaction. or a single step of a complex reaction which proceed a number of steps for its completion. Next point is molecularity of a complex reaction as a whole has no meaning. Molecularity of a complex reaction as a whole has no meaning. Next point is it has a positive value, never zero or fraction. Next point is molecularity of a reaction has a positive value, it is never zero or fraction. Next point is molecularity only applicable to elementary reaction or simple reaction. Next is it is applicable to single step reaction. Last point is it is a theoretical concept. It can be calculated from a simple balanced reaction which proceeds through a single step. Then we discuss about types of molecularity. Next, we discuss about types of molecularity. Next is types of molecularity. As already we have discussed, that is, it has a positive value, only positive value, never zero or fraction. That means molecular value may be 1, 2 or 3. Never it exceeds this value. Molecularity of a reaction never exceeds 3. So there are 3 types of molecularity: unimolecular reaction, bimolecular reaction, trimolecular reaction. We discuss one by one. First is unimolecular reaction. First one is unimolecular reaction. That means depending upon the total number of atoms or ion or molecules that collide effectively at a time to bring about a chemical reaction, molecularity are of 3 types: unimolecular, bimolecular, trimolecular. If a reaction consists of decomposition of one reactant species, then it is known as unimolecular. I repeat again. If a reaction related to or consists of decomposition of one reactant species, then it is known as unimolecular reaction. Suitable example: decomposition of nitrogen pentoxide, decomposition of ammonium nitrite. Mark that. Examples: decomposition of nitrogen pentoxide. Equation is N2O5 give rise to N2O4 plus half O2. Second one is decomposition of ammonium nitrite, NH4NO2. Equation NH4NO2 give rise to N2 plus 2H2. These are some few examples of unimolecular reaction. Then switch over to bimolecular reaction. Next one is bimolecular reaction. Bimolecular reaction. What do you mean by bimolecular reaction? A reaction which consists of collision of two reactant species. A reaction in which there is a two reactant species, involvement of two reactant species whose concentration is changed, that is known as bimolecular reaction. In a simple step reaction, two reactant species there which bring about effective collision to form the product known as bimolecular reaction. For example, dissociation of hydrogen iodide, acid hydrolysis of ester, we discuss, that is dissociation of hydrogen iodide, that is 2Hi give rise to H2 plus I2. Next one is acid hydrolysis of ester, that is CH3COOC2H5 plus H2O in presence of mineral acid to give rise to acetic acid plus ethyl alcohol. Its name is ethyl acetate. It is an ester. Next, acetic acid, that is ethyl alcohol. These are few examples of, that is, bimolecular reaction. Then switch over to trimolecular reaction. Mark that. Next one is trimolecular reaction. Third one is trimolecular reaction. What is a trimolecular reaction? A reaction in which there is the involvement of three reactant species. Collision of three reactant species bring about a product that is known as trimolecular reaction. Suitable examples are oxidation of sulfur dioxide, oxidation of nitric oxide. Examples are oxidation of sulfur dioxide, that is 2SO2 plus O2 give rise to 2SO3. Next one is oxidation of nitric acid, that is 2NO plus O2 give rise to 2NO2. These are some examples of trimolecular reaction. That means we complete what is the molecularity of a reaction, then explanation about molecularity, then characteristics of molecularity, then types of molecularity. Next we discuss about what is the difference between order of a reaction and molecularity of a reaction. Then switch over to, it is a 2-mark question, very very important for council point of view. Distinction between order and molecularity of a reaction. Left side, order of a reaction. Right side, molecularity of a reaction. Mark that. Point 1, definition. Point 1, definition. What is the definition of order of a reaction? It is defined as the sum of the powers, addition of the powers of the molar concentration of reactant species which is represented in a balanced chemical, which is represented in rate law expression. I repeat again. the sum total of the powers of the molar concentration of reactant species, which is represented in a rate law expression. What is the definition of molecularity? It is defined as the number of atoms, ions, or molecules which come together, collide with among themselves effectively at a time to bring about the chemical reaction, is known as molecularity of a reaction. So while going through the distinction between two mark question, always mention first point definition. Move to the second point. That is, order of a reaction refers to as a whole of a reaction, as simple reaction as well as complex reaction. If a complex reaction proceeds number of steps, then molecularity of a order of a single step has no meaning. We calculate order of reaction as a whole. The second point is, it refers to as a whole for an elementary reaction as well as complex reaction. Point 2, it refers to single step reaction, simple reaction or single step reaction, or single step of a complex reaction which proceed a number of steps for its completion. Third point, order of a reaction, it has a positive value, zero or fraction. Order of reaction may be positive, zero or fraction. Its value may be positive, zero or fraction. Third point, its value is always positive. Next, order of a reaction is applicable to simple step as well as complex reaction. Order of reaction applicable to elementary reaction as well as complex reaction. It is applicable to elementary as well as complex reaction. It is applicable to only elementary reaction. Next, last point is there, that is, it is an experimental phenomena. Order of a reaction is an experimental phenomena, while molecularity of a reaction is a theoretical phenomena. Next, switch over to long question, first long question of this chapter, that is zero order kinetics. Next we discuss about the first long question of this chapter, that is kinetics of zero order reaction. That is first long question, that is kinetics of zero order. What do we mean by zero order? A reaction said to be zero order if during the progress of the reaction there is no change in concentration of the reactant. That means rate of reaction is uniform. There is no change in concentration of the reactant. So let us consider a zero order reaction, that is A give rise to product. Then according to rate law, the rate of a reaction, rate of a reaction, that is R, proportional to R, rate of a reaction, that is R, is equal to minus d by dt of molar concentration of A proportional to A naught. A naught is the initial concentration of reactant, or to the power 0, or you can write d minus d by dt of molar concentration of A is directly proportional to A to the power 0, zeroth order, zeroth power of initial concentration, or we can write minus d by dt of A is equal to k into A to the power 0 is equal to k, or d of molar concentration of A is equal to minus k into dt, equation 1. Then integrating both sides of the above equation, integrating both sides of the equation 1, we have integrating both sides of the above equation, we have integration derivative of A is equal to minus k integration of dt, or A is equivalent to minus kt plus c, equation 2. Where C here, C is known as integration constant. We have to calculate the value of C. Next, when t is equal to 0, let us consider that t is equal to 0 means at the time of beginning, the concentration of reactant is a 0. That is known as initial concentration of reactant. So putting this value in the equation, we have A is equal to A naught is equal to minus k into t plus c. Indicate that c is equal to A naught. Putting the value of c from equation 3 in equation 2. Putting the value of c from equation 3 in equation 2, we have putting the value, we have A is equal to minus kt plus A naught, equation 4. Or rearranging this one, or rearranging, we have kt is equal to A naught minus A. Mark that, or k is equal to 1 by t A naught minus A, equation 5. It is known as the kinetic required expression for kinetics of zero order in integrated form. I repeat again, it is the required expression for kinetics of zero order reaction, kinetics of zero order reaction in integrated form. It can be represented in a normal form. So this above equation can be expressed in normal form by putting that is A naught initial concentration, that is A moles per liter, and A, that is final concentration, that is A minus X moles per liter. In above equation, we have put this value in above equation, we have K is equal to 1 by T, that is A minus A plus X. That means K is equal to X by T. Mark that. It is the required expression for zero order kinetics in normal form. Mark that. Next we discuss about some characteristics of zero order reaction. Next we discuss about characteristics of zero order reaction. 3 to 4 points is there. all the zero order reaction must obey this equation. That is, all the zero order reaction must obey this equation as well as this equation. Mark that this equation. What is the equation? That is, I repeat again, that is A is equal to minus KT plus A naught. From equation 4, mark that. I repeat the equation 4. This equation indicates that it is an equation of a straight line in the form of y is equal to mx plus c. Mark that. It is known as y, it is known as m, it is known as x, it is known as c. It is an expression equivalent to, that is, y is equal to mx plus c, equation of a straight line in slope intercept form. So if we plot a graph by taking, y versus x, what is y? That is concentration. What is x? That is time period. If we plot a graph by taking y versus x, then y-intercept slope, y-intercept, this is known as a naught, y-intercept, and the slope m is equal to minus k. Slope of this straight line is minus k. It is an equation of a straight line in the form of y is equal to mx plus c. So from this equation also it is clear that as by definition zero order reaction, rate is independent of initial concentration. So if we plot a graph by taking rate versus concentration, then we have like this one. By definition, rate, the concentration does not affect to the rate of reaction. So it is an equation of a straight line, that is, which is parallel to x-axis. Next we discuss half-life of a zero order reaction. Next we discuss half-life period or half-life time for a zero order reaction. Half-life time. Symbol is T1 by 2, T half or T 50%. What do you mean by half-life period? It is the time during which, after which, the concentration, initial concentration reduced to half, the final concentration reduced to half of its initial value. I repeat again. What do you mean by half-life period? It is defined as the time after which, it is defined as the time during which final concentration reduced to half. So mark that. That means, I repeat again, it is defined as the time during which final concentration is reduced to half of its initial value. That means when T is equal to T half, initial concentration A equivalent to A by 2. So putting this value in the previous equation, what is the previous equation? Previous equation is K is equal to X by T. Mark that. It is the previous equation. If we put this value, that is T, if we put instead of T is T half, then we represent the initial concentration, that is A by 2, then it becomes K is equal to A by 2 T half, or T half is equal to A by 2K. Mark that. From this expression it is clear that the half-life period of a first order reaction, from this expression it is clear that the half-life period of a zero order reaction is directly proportional to the initial concentration. So if we represent this one, mark that, if we rewrite T half is equal to A into 1 by 2k plus 0. Mark that. If we rewrite this equation in this way, then it represent equation of a straight line in the form of y is equal to mx plus c. Mark that. It is known as y. It is known as m. It is x. It is c. So if we plot a graph by taking y versus x, mark that. If we plot a graph by taking half-life versus initial concentration, then equation of a straight line is like this, while slope m is equal to 1 by 2k. These are some mathematical expression and graphical representation relating to zero reaction. Last one is unit of the rate constant for zero reaction. What is the unit of a rate constant for zero reaction? We know that for nth order the value is moles per liter to the power 1 minus n dot second inverse. For zero order it becomes 0. Putting this value, that is k is equal to moles per liter per second inverse. So, in class 3 of the chapter Chemical Kinetics, today we cover molecularity of a reaction, characteristics of molecularity, types of molecularity, difference between order and molecularity of a reaction. Next, the first long question, that is kinetics of zero order reaction and the half-life period, and some mathematical expression and graphical expression relating